Hello everyone. I just wanted to go over auto-tuning because even though there's not going to be a module on this or even an assignment or anything like that, it was definitely a crowd pleaser today. And I want to make sure that everybody knows how to run code to do this sort of thing if they want to play around with it on their own. So just to remind of the effect that we're going for, so here's Cher's Believe, where she pioneered an artistic use of auto-tuning. So here's the chorus with a little bit of reverb. And now she's going to use Autotuner. So what we're doing is, I call it discretizing pitch. So what we're doing is rounding notes somehow, or rounding notes to the nearest allowed note in a particular scale. That's what we're doing. In order to do that, though, we need to actually know what note is playing. And so a sub-problem that we have to solve is something called fundamental frequency tracking, or F0 estimation, as a lot of people call it. And so in this case, we want to know what note is somebody singing, what is the frequency of the bass frequency that the person is singing. F0 estimation is more general than singing and can also apply to different instruments. But here we're applying it to voice. And so let's say that we had this little clip of Marvin Gaye here.
Ooh, I bet you're wondering how I knew.
So eventually I will work on a little auto-tuner for that. But first, what I'm going to do is take the spectrogram and actually use something in the Labrosa library called the probabilistic yin technique for fundamental frequency tracking. And just to show you what that looks like on top of the spectrogram, here it is. So it's showing in cyan what it thought was the fundamental frequency of the singing over time. And, I'm not telling you all the details of how this works, but you certainly do know a lot about how this works given what you did for tempo estimation and beat tracking. So in tempo estimation, we used autocorrelation of the audio novelty function to estimate tempo. And then in beat tracking, we used the Viterbi algorithm. That's what it was called when we computed the C-score and the backlinks, to compute the locations of beats while making sure that we fit the audio novelty function, but that we also kept tempo. So we traded off between measurement probability, so this was the audio novelty function, and transition probability. So this was the staying on tempo. So we kind of said, okay, I want both of those things to be true to some extent, and so maybe I will miss a tempting peak in the audio novelty function to continue on to stay on tempo. Or maybe I go off tempo a little bit to get this really good peak in novelty function. And it's a global optimization, so we're going to look over all possible beats and find all the beats that maximize. So it uses something called dynamic programming. This is the Viterbi algorithm. Okay. In fundamental frequency tracking in this way with yin, so in F0 tracking with yin, or probabilistic yin, we do autocorrelation again to estimate the fundamental frequency, but on the raw audio this time. So before we had crunched on the audio a little bit and actually computed the audio novelty function first. Now we actually do autocorrelation in little windows of the raw audio. And then the transition probability this time is if a note is still sustained, we don't expect the fundamental frequency to jump too much. from window to window. We also allow for the possibility that a note is no longer active. So maybe they're not singing anymore. Okay, so in Librosa, a not note is represented as a nan. Okay, so if I'm not playing the note, then I don't have to worry so much about what the maximum is in autocorrelation. But if I'm going along, then I don't want to jump around too much, okay? And so then it's a very similar algorithm to what we did for beat tracking, actually. So I'm not going to go through the details, but we can treat this as a black box for now, knowing some of the intuition about how this works. Okay. So what we get back is this array. It has as many elements as there are columns in the short-time Fourier transform. And if it doesn't think that there's a note happening, it gives a nan. And when you go to plot nans in Matplotlib, it just doesn't plot anything. And that looks reasonable. Yeah, you can see there was a little gap there, and then he stopped right before the end. Okay. But one other thing, rather than looking at this, we can say, okay, yeah, this looks reasonable. We can also listen to it. And it's, I've shown on a variety of occasions in this class, it's great to come up with these sonifications. So to hear what is it that the computer has actually learned here. And so a natural sonification for this is just to create a pure tone, or maybe something in between a pure tone and a square wave. That's what I did here. That has the same frequency as F0. So what I'll do is I say, okay, actually every one of the windows where we have a pitch estimate is within a number of audio samples equal to hop length. And so what I'll do is I say, okay, well, there's n frequency estimates that came out of probabilistic yin from Librosa. So that means that I have n times hop length samples total that I need to fill in. So what I'll do is I'll loop through all the frequencies, and then I will say, all right, let's make the instantaneous frequency from sample I times the hop length to sample I plus 1 times the hop length be the whatever that frequency was at index I. And so that's the instantaneous frequency. Now, of course, remember when we talked about chirps, we have to integrate this to go back to an actual sinusoid that changes frequency over time. And so this is just a numerical integration here, like I showed back in module 3 or 4. Okay, so let's listen. Oh, nothing happened. I got to be a little bit careful here. There's some nans. And so I got to make sure, okay, I'm only going to actually put anything there if it's not nan. So there we go. There's Marvin Gaye as somewhere between a cosine and a square wave. So that's pretty cool. And I guess if I wanted to, I could even put them up an octave. So I could multiply this by 2. There we have it. Cool. All right. Now, so it seems like the fundamental frequency estimation is working pretty well, at least on this example. So now we can start to try to apply it to auto-tuning, right? So as I said towards the beginning, what we want to do is round the notes to the nearest allowable note on a particular scale. Now, just for now, what I'll do is I'll round it to the nearest actual note in terms of note number. So maybe I'll allow the entire chromatic scale for now, so all possible notes. But that they're still discrete. Not every frequency is covered by them. So remember, we have the equation that is the frequency of a particular note number P is equal to 440 times 2 raised to the note number P over 12. And so if I can invert this, so what I can do is solve for the note number associated to a particular frequency, which may or may not be an integer. These are supposed to be integers, but we're getting a particular frequency estimate, which may not actually be an integer. So let me solve for that note number. And as I was showing, what we can do is, okay, we can divide both sides by 440. So I get f over 440 is equal to 2 raised to the p over 12. And then I can simplify that by taking the log base 2 of both sides. So then I get log base 2 of f over 440. Well, the log base 2 cancels out the 2 exponential, so that's p over 12. And then finally, I can solve for p, and I can say p is equal to 12 times log base 2 of that frequency over 440. All right, so that's my equation. And so what I'll do is I'll make, okay, I'll say that, first I'll compute this note number. I'll say p is equal to 12 times log of the max freaks over 440. So those are the frequencies that I got from pi yin, or from p yin about tracking this. And then what I'll do is I'll round. I'll say, okay, let's round to the nearest integer. So round each note number to the nearest integer. Now I have to go back and I have to say, all right, well, let's make the max frequencies rounded to be, I'm just going to apply the original formula. So that should be 440 times 2 raised to the p over 12. And now if I plot these both next to each other, we see what we get. Let's see, is that right? Oh, I meant to do log base 2. Okay. Yeah, that's important. So let me not forget that base 2 there. Okay, so anyway, now I see, in the rounded version, I have something that follows the original, but it jumps, right, in this kind of staircase pattern, because we have discrete frequencies that which allowed note numbers actually exist. And if we're between them, we're supposed to round to the nearest one. So let's hear what that sounds like, at least when it comes to a sonification. In a moment, we'll try to actually get Marvin Gaye's voice to do the same thing. Okay, so a little bit of hysteresis at the end, a little bit of, maybe it changed a little bit too much towards the end, but overall pretty good. So we got that kind of effect that we saw a moment ago with Cher, right? Okay. So here's what we do to apply this to the spectrogram. So what I'll do is actually take the ratio of the frequency that I'm trying to be at, so the ratio of this orange curve to the blue curve. And so if the orange curve is below the blue curve, that means that I need to move down in frequency. I should be multiplying all the frequencies by that factor. If the orange curve is above the blue curve, then I need to actually scale all of the frequencies up, right? So every frequency, not just the fundamental frequency, but every single frequency on the spectrogram. So what you do is you actually interpolate. So there's a method in NumPy that interpolates the domain of a particular function. And so this is just saying I want the new frequencies to pull from the old frequencies over the ratio. And I'm going to warp each column individually depending on what that ratio is, because it's going to change time to time how much I need to move up or down. So if I listen to this,
Ooh, I bet you're wondering how I knew.
So there it is. That's the auto-tuned Marvin Gaye there.
Ooh, I bet you're wondering how I knew.
Now, I can do something even crazier than this. So let me encapsulate this in a method. So maybe I'll say def do auto-tune. Let's see. We take in the spectrogram. We'll take in. I guess we'll take in max freaks, and then maybe I'll call it target or something. Okay. So I'm going to take in the spectrogram. I'm taking max freaks. And then so I'm going to say, okay, ratios is equal to, so the ratio is going to be the target over what the frequencies were. And I think I have all the information I need here. So let me just, oh yeah, and I forgot to mention, I'm doing Griffin Lim because I'm actually, shifting the the frequencies up a little bit or down a little bit in the entire column of the spectrogram. So, okay, let's say y shift is equal to do autotune s max freaks. And so here the target was max freaks round. So let's try this. So yeah, I had a Griffin limb implementation here. So that seems okay. Okay, but now see the really fun thing I can do. What if I insist that the target frequency is concert A, or this is 440 hertz everywhere? Okay. So what I'll do is, instead of passing along this orange curve, I'll just pass along curves that's flat 440 the whole way through. So let's listen to that. So if I make my target be, so I'll say 440 times mp.1s, and I'll make as many ones as there are max freaks. Let's see what that sounds like.
You wondering how I knew.
So you could tune your orchestra to Marvin Gaye because he's singing, you know, perfectly the 440A the whole time.
Ooh, I bet you wondering how I knew.
So there's Marvin Gaye in a monotone. Maybe I'll move it down a little bit. Let's go maybe down to 330, which is an E below that A.
Ooh, I bet you wondering how I knew.
So, yeah, okay, I'll put two different entries in the notebook here. So there's concert A, and then here's the E below A. Here is a 330 hertz E3 note. So anyway, that kind of blew my mind. You know, we usually Autotuner usually just moves pretty close to where you already were. But there's nothing stopping me from doing something radically different here.
Ooh, I bet you wondering how I knew.
The problem, of course, is that I could either get chipmunk voice or, you know, the very slow, lethargic voice. So you have to do more work if you want to avoid that. But in terms of you know, singing the song and staying at a particular pitch, we certainly got that.
Ooh, I bet you wondering how I knew.
But yeah, the normal application is to round to the nearest note in a scale. So here's just rounding to the nearest note in the chromatic scale again.
Ooh, I bet you wondering how I knew.
So there you have it. That's auto-tuning. So yeah, if you want to try this, you know, I put the code up on. I'll put a link to the code. I mean the only thing that you need beyond what I did is just there's this file where I implemented Griffin limb to invert the spectrogram. So, I mean, you can do that, and it's also actually kind of technically part of the next homework. So, anyway, cool. So yeah, I hope you have fun with this. If you do anything fun with it, post on Discord. Let us know. Enjoy.